Good afternoon, everyone. This is Mark Albert, Editor-in-Chief of Modern Machine Shop Magazine. Welcome to our webinar sponsored by Modern Machine Shop and FANUC FA America. Thank you for joining us. Our topic this afternoon is easy integration of advanced CNC features. Reducing cycle times, increasing accuracy, and reducing costs are important manufacturing topics to evaluate regularly. Today, we'll discuss how you can quickly achieve all three with a few simple process changes. We'll focus on 4, 5, or more Axis applications and take a brief overview of the CAD-CAM-post process, changes to the CNC setup, and cost-effective accuracy improvement techniques that can have a dramatic effect on manufacturing efficiency. Our presenter is Rick Schultz. Rick is currently Aerospace Program Manager with a focus on aerostructures at FANUC FA America. Rick drives advanced CNC technology into the aerospace industry to help it increase manufacturing efficiency, improve manufacturing accuracy, and reduce production costs. Rick has been in the machine tool and aerospace industries for 23 years and has extensive experience with 5-axis applications, high-speed machining, hard metal machining, and composite manufacturing. In the past, I've worked with Rick on several editorial projects, so I know he's a real expert in advanced machining. As we listen to Rick and follow along with his presentation, please feel free to share your questions with us by typing them in the questions pane on your control panel. Rick will answer those questions at the end of his presentation. Please keep in mind this webinar is being recorded, so you'll be able to view the entire program online later. Again, thanks for taking time with us today for this live program. Here's Rick.
Hey, thanks, Mark. Thanks for tuning in, everybody. Like Mark said, we're going to do a real quick overview of a lot of the advanced features and how to best apply them so that you can become more efficient and a little bit more cost-effective in your operation. In general, if the answer to any of the questions that you see are yes, there's information that I'll provide that we can definitely help you with and help you become more efficient and as a result make a little bit more money. A couple examples are if you have expensive post-processors that you have to maintain, if you spend a lot of money and a lot of time having to modify your post-processors, if you have different vintage controls and you have, as a result, have a different post-processor for each vintage control, there are things that we can do to help. We can also do a couple little things to help reduce your cycle times and help your parts be a little bit more accurate. There's a lot of amazing technology in today's CNCs. A couple things that a lot of people don't take advantage of that are available to you are simple things, like instead of programming the machine specifically using the machine coordinate systems, you can program the part directly, which makes it so your part is now independent of the machine, meaning that you can cut that same part on almost any machine capable of holding that size of a part. There's all types of advanced NURBS algorithms and fairing tools to help you make a much higher, much shorter cycle time, much higher feed part. Features like high-speed smooth TCP, advanced contour control, all of these things can help you make a much more efficient manufacturing system, and as a result, be outputting higher accuracy parts, as well as reducing your cycle times and becoming more efficient. Now, when I talk about these, there are some quality differences in systems out there, and if you wanted to do things perfectly, you would invest a lot of money and a lot of time in optimal tooling and the highest end CAD-CAM systems you can get in a mechanically perfect machine. Now, this isn't very practical for several reasons. For one, an optimal setup would involve programming the CNC utilizing the native interpolation language, which is typically a NURBS spline algorithm. That's a syntax that hardly anybody knows how to look at and view. Everybody, however, knows how to look at and view traditional G-code. There's also issues where the number of people out there in the industry that are available to support you with these complex systems is very limited, because you have to hunt for a specific expert on a specific system as opposed to utilizing the vast amount of resources available in the industry to help you with traditional G-code programming and CNC operation. Now, the majority of the CNCs that are out there in the industry today are still utilizing traditional processes. And by that I mean they're still being programmed the same way they were 20 years ago. Now, what you can do is you can balance the theoretical perfection that I just discussed, meaning taking advantage of advanced spline algorithms and stuff, with practical, sustainable, and affordable solutions. To do this, I'm going to try to help you identify and make a couple very simple improvements that are very easy to implement that will give you very large return on your investment in time. Now, the typical process that everyone follows today for complex parts is you have a CAD system where you generate your part model. You have a CAM system that effectively does a dot-to-dot approximation of that part model. And you have a post-processor that will format those dots into a specific control machine setup. And then ultimately the CNC will take the output of the post-processor and basically connect the dots that are sent to it. Now, when you look at that process, it's actually a very inaccurate, non-efficient process. Because as you look at the graphic on the screen, the red line is your CAD model. It's a beautiful, smooth curve. Your CAM system then generates an approximation of that by taking a tolerance value that, as the programmer, you define. It's typically called the in-tall-out-tall. And then the CAM system will create a series of points within that tolerance band along the surface of your part. By the time that gets to the CNC is going to try to do exactly what is sent to it. So what you'll end up with is that black line that you see on the screen, with a bunch of straight lines going between all of the dots generated by the CAM system. Now, typically, that isn't what you want your machine to be doing. So you do all types of little compromises, like flooding your part with more points to try to minimize the amount of deviation of the points from the actual surface, in this case the red line. You also do things like you detune your servos and actually make your machine less responsive, because you don't want it to be so responsive that the end machine motion at the tooltip is that exact black line, because you never actually want to do that very rough, coarse path that you see. You want to do something that more closely approximates that nice smooth red line that came out of your CAD system. Now, in a 5-axis application, the problem is significantly worse, because using traditional programming technology, you aren't programming the tool tip, so you aren't programming the location where the tool actually touches the part. You're programming the point somewhere up in your kinematic chain. By doing that, the CNC, when it receives the series of points by the CAM system, is actually going to scallop between every one of those points. If you go up to wherever the programmed point is, using the traditional programming methodology, you'll see the straight lines, but the net effect with 4 or 5 axes at the tooltip is that you'll actually scallop between every one of those points. A lot of times that scalloping is mistaken for faceting, and some of the common solutions for that is flooding it with more points or detuning the machine, as I described a little bit earlier. One of the first features that's important to utilize, if you aren't utilizing it today, is changing your mindset from machine coordinates to part coordinates. And in a FANUC control in particular, you do that by utilizing a feature called workpiece setting error correction. Now, what that feature does is it allows you to define wherever your part coordinate system is and then execute the same program. So in the graphic that you see, if I have a perfect fixture, as what's represented in the left graphic, I hit cycle start and it'll go through the part and execute it just fine. However, if I have an imperfect fixture with a little bit of rotation or on a completely different location of the table, like what you see on the right graphic, I can run that exact same part program by utilizing a feature like workpiece heading and error correction. Now, we do have another feature if you have additional facets on that part where you need to do a local operation like a drilling cycle or a pocketing pattern. In FANUC, we call that tilted working plane. Now, utilizing features like this for your part geometry, you end up with significantly lower labor costs because your operators and your setup staff aren't spending significant amount of time trying to shim the part and adjust everything into a perfect fixture. And it also simplifies your programming process because now you're programming the part as opposed to programming the machine. Another feature that's important to make sure you're taking advantage of, in 4 axes or more, is tool center point programming. And what that means is instead of all of my G codes, my X, Y, Z coordinates inside my part program, those represent effectively the tool center point, which is in most practical cases the contact point of the tool to the part. So rather than programming the machine, I'm actually programming where I want my tool to touch my part. And then I let the control take care of all the math to make sure that the tool ends up at that proper location. There's another feature called tool posture control, which is similar to tool center point control, but it affects the side of the tool. So if you're doing side mill cutting like what's shown in the graphic on the right, going around a cone, you would want to have tool posture control also. Otherwise, you would end up with scalloping all the way around the part. By utilizing these features, you eliminate that scalloping effect either at the tool tip or on the tool side. And you can also dramatically simplify your post-processor, and I'll go into a little bit more detail on that later. It also makes your part program machine independent. So regardless of whether I have a CA or a CB type head, I can run the exact same part program. By making it be a smooth path, I can also achieve higher actual feed rates. A lot of times you'll program 100 inches per minute, but then out there at the machine when you watch the part execute, you'll find that you're only achieving 60 inches per minute or so. A lot of that is caused by the acceleration and deceleration that occurs when you aren't telling the control to do a smooth path, like what you see at the bottom graphic. Instead, if I'm commanding the faceting that you see at the top graphic by not utilizing features like tool center point and tool posture control, the control has to do a lot of acceleration, deceleration, and as a result, I may never achieve my programmed feed rate. Now, one of the important features that most people don't take advantage of is a real-time spline interpolation look-ahead algorithm. And what this does is when my CAM system spits out a series of points, like what you see in that graphic, instead of the control trying to execute the black line connecting the dots of the points that are sent from the CAM system, the control interprets that series of points as a spline curve, effectively recreating the initial surface that my CAD system defined. By utilizing a feature like that, I can now go through that significantly faster. Almost direct analogy is a race car. If you see the graphic down at the bottom right, if I tell my machine to try to follow that red line or the race car driver to follow the red dashed line, he's going to have to significantly slow down to stay on path. However, if I tell him to follow the green line, which is a much more optimal path, he's going to be able to go through those curves at a significantly higher speed. The same thing is true at your tooltip. If you're telling the CNC that you want to execute the blue line in the graphic up above as opposed to the black line in the dots, you will be able to run significantly faster and achieve the programmed feed rates that you set in your G code, which will result in shorter cycle times. It allows the machine tool builder to more highly tune his servos, so you're running at a much higher gain, which means you have less following error, which as a result means that you're significantly more accurate also. Another technology that a lot of people don't take advantage of is utilizing process-specific settings. In the FANUC control, we call it machining condition selection function. And what this gives you is effectively 10 sets of path definition parameters. So I can define a acceleration and jerk rate and maximum cut feed rate for a roughing pass, and then have a second configuration set up for a finishing pass. Easy way to think of it is in my roughing passes, I'm less worried about accuracy and more worried about just blowing through the material and removing as much material as I can as quickly as I can. So I would have a very aggressive acceleration rate and a very aggressive profile as a whole. Whereas on my finishing pass, I want to be a little bit more careful going around a lot of the surfaces and stuff that are defined by my G-code. So I have a much lower acceleration rate and a much lower maximum cut feed rate, as an example. Another way that this can be utilized that a lot of people don't think about is if you have specific materials that you're trying to cut on the same machine, because you have limited resources available to you, and you have two jobs, one of them being a hard metal job and the other one being a soft metal job. You could effectively set up this machining condition selection function so that R3, as an example, might be a pretty aggressive acceleration rate that makes sense when you're cutting through aluminum. But then R7 or 8 is a much more conservative acceleration rate that would make more sense when you're cutting through titanium. Now, you can cut both on the same machine without doing a drastic reconfigure or drastic changes to my machine and control setup. A programming methodology that I'm a big proponent of is modular programming. Just like this is true for traditional software programming on a computer, it's also true for programming on a CNC. And the basic flow that I follow is the 4 bullets that you see at the top. I have a section where I locate the part. I have another section where I activate all of the features that I want to have active as I go through my geometry. And then I have my actual part definition, which is the output of the CAM system. Whenever I need to stop producing the part, either for a tool change or for end of program, I deactivate all of the features to put it back into a safe state, and then I would restart by doing the feature activation setup again, and then going back into the next section of the geometry. Now, what this methodology does is it makes it very easy for you to support this part through the future. So as new features come available, as new control vintages come available, you can very quickly adapt your existing program to your new setups, to your new machines, or to your new feature sets. And as an example, if you look at the code on the left, that would be my core part program. And you can see that the only specific codes in there are down in the middle section, and that's what defines my part. So that's basically my CAM data that says, here's what I need my G1s and my G0s to be to produce this part. As I described earlier, we make it all in part coordinates by utilizing features like our workpiece setting error correction. And we also do everything we can to keep the geometry part independent by utilizing available features like vector programming, which I'll touch in a little bit more detail on that in a second too. If you look at the program flow, I have a macro at the beginning that effectively calls my part location that does whatever it needs to do from a probing standpoint to go out and touch off the part and set up my offset tables appropriately. Then I call another macro which activates the features that I plan on utilizing on this specific machine to produce my part. Then I have my CAM data in the middle, and then I have a deactivation macro at the end that disables all of the functions that I activated. Now, on another vintage machine, I may not have this exact same feature set. As an example, I may not have fairing, which you can see is one of the last lines of the activation macro. So I would have a different macro loaded in that machine than I do in the machine that has that feature available. Now my core part program is identical. I have different activation macros in each machine. I can run the exact same core part program on either machine without modification now. So that's the primary benefit, is I've made it so that my part programs truly define the part geometry as opposed to defining how to cut the part on my specific machine. With this, and with features like vector programming, you can severely simplify your post-processor. And this is one of the nice effects of utilizing a lot of the advanced features. If you look at the output data of your CAM system, you're going to see a line like what you see at the top of that page. It'll be a go-to slash and then a series of numbers. Now those numbers are the point, approximated point on the surface of the part. The CNC can understand that data directly, so your post-processor only needs to reformat that data. And you can see an example of that up above, where instead of having a lot of complex math to translate the XYZ coordinates to a specific machine, or a lot of complex math to translate the IJK tool orientation vector to a specific machine head kinematic, I can just input that data directly to my CNC and execute it and get the same part. What that does is that simplifies the post-processor to the point where there is no extensive support required, because all you're doing is reformatting the data that comes out of your CAM system. You've taken a lot of the logic, which is where a lot of the pain comes from, out of the post-process. What you've done is you've turned your post-processor into a simple reformatter. By doing this, you'll have a little bit better accuracy. The machine geometry section of your part programs will be completely machine independent, and you'll get the easier long-term program support that I described earlier. From an accuracy standpoint, if you utilize all these features, such as the spline interpolation, tool center point control, tool posture control, and so on, you'll have a much smoother path, which as a result means that you'll be able to increase the responsiveness of your machine, which in turn will give you better accuracy as a whole. There's also other things that you can do to improve your accuracy beyond just getting your machine to be more responsive. A couple examples are, one of the big catchphrases today is volumetric compensation. I generally recommend that people follow the flow that you see on the screen there, where first, get your pitch error compensations correct. Get every single axis to be as accurate as possible. On a 4 or 5 axis machine, make sure that the kinematic is calibrated regularly. That's highlighted in red because the majority of the time, the values in the control for the kinematic are actually the nominal print values for the machine, as opposed to the actual measured values on the machine. After getting those two resolved, I typically recommend going to a more basic volumetric compensation system that picks up beam sag, straightness, squareness, all of the other simple mechanical compensations that you used to stack, rather than stacking all of those compensations and creating a support nightmare for yourself. A single function like FANUC 3D can pick up and resolve all of those mechanical errors. After you've taken care of straightness and squareness and those issues by utilizing a FANUC 3D style function, you got to deal with thermal growth and find a good way to resolve your thermal growth error before you dive into a more advanced feature, which is what is typically referred to as volumetric compensation in the industry, such as the FANUC 3D rec function. It stands for three-dimensional rotary error compensation. We have a lot of expertise and a lot of resources available to help you with this process. So rather than go into a lot of detail now, I'd recommend if you're looking to improve your accuracy that you contact us, and we'll be more than happy to help you through the process. A couple of other resources that we have available to help you out is we have a lot of free workshops where we'll come out and we'll help your programmers take advantage of the features that I described briefly earlier in this presentation. We'll come out and actually look at the specific types of parts that you're cutting and give you our recommendations on how to change it and adopt some of the best practices for part programming and utilize some of the advanced features available to them. We also have free specification and runoff consulting, where if you're getting ready to purchase a new machine, we'll come out and we'll help you write the specification so that you can make sure that what you get when you purchase the machine is exactly what we recommend. And then we also have a lot of manufacturing support services like maintenance workshops, where we'll come out and we'll do a quick 4-hour maintenance refresher for all of your support staff to make sure they know what tools are available to them and what resources are available to help them get out of any problem that they may encounter. And we also have another service where we'll come out and we'll do a complete inventory of all of the FANUC components throughout your facility, regardless of the number of machines. And that can be a great help, not just from an understanding what you have on your floor, but by having that visibility, we can determine what's missing on some of the machines so that you have a more consistent programming methodology across your entire operation. This is the primary contact information. To go into more detail and find ways that we can help you become more efficient and utilize a lot of the advanced features, you can always call 188-FANUC-US, or you can contact me directly by sending me an email at rick.schultz@fanucfa.com. An example of a lot of these features in use that goes into much greater detail than we can do justice in a short webinar is the recent May 2012 Modern Machine Shop issue, where they describe in detail vector programming and the benefits that they achieved by utilizing not just vector programming, but a lot of the features that I described a little bit earlier. So I highly recommend that you grab a copy of that if you don't already have one. And with that, that's the end of the brief overview. So I think we're ready to open the floor for questions.
Okay, great. Thank you very much. That was a really interesting presentation. So, yeah, and we do have some questions already from our audience. So we'll get started with those. In the meantime, please feel free to submit your own questions by typing them into the question pane on your control panel at the right of your screen. Now, we'll get answers for all of your questions, even if we don't get to them while we're on the air. So remember, this webinar is being recorded and it will be available online. So if you can't stay for the whole session, you can catch up later. So let me jump in with these questions here. Okay, one attendee wants to know, says, I currently use FANUC's rotary table dynamic fixture offset. How does that work with these features?
Yeah, that's a question that I get all the time. And basically, that feature is replaced by utilizing tool center point control, tool posture control, and our work piece setting error compensation. That's a much better solution, and I'd be happy to come out and walk people through the benefits and how much improved that feature set is versus the original rotary table dynamic fixture offset style approach.
Okay. Another question here is, I have nano smoothing today, but noticed you didn't mention it in the presentation. How does that apply?
Nano smoothing is our older real-time spline look-ahead function, and it works really well in our existing platform. So if you're looking at any model really that has an eye after it, like a 15i or a 16i, to do the spline look-ahead, we would utilize nano smoothing. We have a newer feature called high-speed smooth TCP that has a different algorithm in it that mathematically works out a little bit better than the original spline algorithm utilized by nano smoothing and some of the other competitive spline algorithms. And so for newer applications, I'd recommend looking at high-speed smooth TCP with fairing as opposed to looking at our older nano smoothing function.
Okay. There's a question here. Doesn't spline affect contour accuracy?
Not really. It should make it better. If you look at everything as a system instead of looking at it as a single function, by going with a spline, it's true that you aren't necessarily going to go through the programmed points. And I just brought the slide back up that shows that. But your end accuracy is actually significantly better because you didn't plan on going through those points to begin with. Those points were an approximation of the actual surface that you wanted to achieve by your CAM system. Doing the spline look ahead will effectively recreate that original surface, so it'll be more accurate. Since you have a much smoother curve, you can also crank up your responsiveness of your machine, which will also increase your accuracy. So in the end, splines will improve your accuracy rather than detract from it.
Okay. Rick, this question is, I like the modular programming design you showed, but my programs have multiple tool changes. How would I handle tool changes?
The way that I typically do them is I would start the same way that I show here. So the beginning of my program is exactly what I have. And then before my M30 at the end, in this example, I would have my deactivation macro, then my M6 tool change. Then I would call the activation macro again, which in this example is a G65 P9006, and just continue to repeat that process until I effectively end the part. So hopefully that made sense.
Yeah, okay. This might be an easier question. Does any of this apply to 3-axis, 3+2-axis, or 4-axis processes?
Yeah, anytime you're doing positioning in motion, if you remember the race car graphic that I just brought back up on the screen, anytime you're doing motion, you want to do motion in the optimal way. Now, from a traditional lathe motion, typically you aren't going to see dramatic improvement. But from the milling side, since you mentioned mill turn, I think, from the milling side, anytime you're doing a contour, these feature sets and spline look-aheads and all of those will give you improvement. So my general philosophy is if you're doing motion, do the optimal motion every time.
Okay. Question, I am very interested in vector programming for 5-axis machining. Do you think this is a good approach?
Absolutely. And that's one of the things where I recommend that you grab that article in the May issue of Modern Machine Shop and give that a good look, because that has a good real-world practical application perspective on vector programming. A couple of things to keep in mind before making the leap. With vector programming, you have to remember that a specific IJK set of values has 2 solutions. So you always have to make sure that you can handle it if the control takes the alternate path to achieve that orientation. You also have to be a little bit careful of singularities. As a quick example of what I mean by a singularity, that's when, let's say you have a CA head on the machine, on a gantry-style machine. If the A-axis is exactly vertical, in this case, the C-axis could be at any orientation. And that's the definition of a singularity, is that there's an infinite number of solutions for the defined orientation. So you have to make sure that when you're doing the programming that you allow for or find solutions for the alternate, the second vector path, and also have yourself parameterized and set up so that you avoid a singularity style situation. Yeah, but if you do that, I'm a big proponent of vector programming.
Okay. Thanks, Rick. Yeah, I've got a couple more questions here, but I just want to remind the audience that we have plenty of time, so please keep the questions coming. In the meantime, let's jump into this one. Does volumetric compensation eliminate the need for other error compensations like pitch error comp?
Well, in In theory, it can. That's one of the differences between when I talk about technical perfection versus reality. In theory, yeah. In practice, no, because the error, if you look at the resolution of error in a pitch error application, you have to do that at a very high resolution to correct. And if you look at the tables that you get after you do a pitch error comp shoot, it'll look like an earthquake happened along the way. You'll see all types of jitter and stuff. To do volumetric compensation, you typically have to measure the entire volume as opposed to a single axis. In capturing the entire volume at the level of resolution necessary to pick up all of that error that you typically see in a pitch error plot, it becomes impractical because it takes way too long to capture that many points. So my general philosophy from a practical standpoint is do the pitch error comp, get every axis as accurate as you can to get rid of that high resolution error, and then utilize the volumetric comp on top of that to take care of the broader errors that you'll find on a machine.
Okay, thanks, Rick. This question isn't so much about what you just explained, but I think just the general presentation. Would this information apply to a CNC drill press machine as well as a CNC vertical turret lathe?
Yeah, kind of like what I mentioned a little bit earlier, where anytime you're doing motion, even if you're just doing drilling operations, I still say always utilize the optimal path. Even if you're just driving in your car to the grocery store, I'd recommend going there the shortest way possible and the smoothest way possible, as opposed to using a car with a steering wheel that has 10-degree increments in it. So regardless of the end process, I typically recommend utilizing the features described here so that you always have that optimal path defined.
Okay, good. Thank you. Another question came in. Does FANUC staff help in choosing the best inserts for cutting different materials?
We'll help you with pretty much every aspect of your operation, really, but we don't have the expertise to give you a direct answer on tooling inserts. However, we have very close relationships with all of the tooling suppliers. So if you ask us to help with that, what we would do is we would consult with our tooling suppliers, who are the experts there, to pick the proper tool for your job.
Okay. This is my question. You also work, FANUC also works with the major CAD-CAM companies too in developing, post-processors and the software tools that shops need.
Absolutely. We've got partnerships with all of the major players in the industry. So basically, if you have a CAD-CAM system, just ask us, and we'll make sure that we've got the right contacts in place to support your operation.
Okay, all right, great. Actually, that was good and lead into this question. And are you familiar with ShopTalk software, and how is it compatible with FANUC controls?
Yeah, I am. The ShopTalk software is more of a simplified conversational system rather than a traditional CAD-CAM system. So the majority of the parts that you define with that are going to be simpler parts where you aren't necessarily doing very complex geometries. However, that being said, anytime you're doing motion, I would recommend that you get your ShopTalk system set up so that when it outputs the G-code, that you're still taking advantage of all of the practices and all of the programming features described here.
Okay. Again, we still have some time to go, so please don't hold back. Ask questions. We've got a few more to go, but there's time for some additional questions after that. The next question that's already in is, how much benefit would this have for just basic turning? We utilize mainly mill turn machines.
I think I mentioned it a little bit earlier with the basic turning profiles. a lot of times you're doing very small steps into the spinning part. So the overall improvement of the turning aspect might not be dramatic. However, if you're utilizing mill turn machines, which I think we already had a slight question on, the milling process is involved, especially if there's a contour, you can see significant improvement.
Okay, great. Question, how do you verify programs using these methods? Now, I know you could do a whole hour webinar just on, program verification, but maybe we could take a crack at that.
Yeah, well, most of the verification systems are really good for giving you an approximation and a very rough crash detection of your process. One of the things where they all fall a little bit short is if you do have a slight orientation change, you may get a completely different motion out of your kinematic than what you saw in your nominal fixture simulation at your desk. So you always have to keep that in mind, that the bulk of what you're doing with your verification software is getting a rough idea, make sure that your part is what you expect, and make sure you don't have any silly crash situations where you're going to just jam the entire spindle into the part. So these features generally aren't simulated in most of those verification packages, but they don't really need to be. Because, again, the goal of the verification package is more basic safety, basic crash protection, and make sure that at the end of the manufacturing, your part is going to look like what you expect.
Okay. Rick, another question here is, on average, what are the production gains achieved with these features?
On average, if you're going from a traditional programming methodology, especially one where you're utilizing a programming methodology called inverse time, you can see dramatic improvement in talking on the order of 50% cycle time reduction. If you're already utilizing features like tool center point control, but you aren't utilizing the spline look-ahead algorithms, you'll still see improvement, but it'll be more on the order of a 10% to 15% style cycle time reduction.
Okay, yeah, that's significant. All right, thanks, Rick. Okay, looks like I'm going to have to make this the last question for this afternoon session. And this question is, I'm getting ready to retrofit a few machines in my shop. How can I make sure I have the right features?
As I mentioned a little bit earlier, if you're getting ready to purchase a new machine or getting ready to retrofit an existing machine, contact us, because we'll come out and help you write the specification and also write a qualification test with you to make sure that all of the features that are specified are set up properly and operating as they should. So the best answer is contact us, get us involved early. Don't wait until you've already signed off on the machine or already cut a check to call us in to help make sure everything's working the way it should. As soon as you think you might have a retrofit opportunity or might have a new machine purchase in the future, contact us and let us help. We'll be more than happy to come out.
Okay, that's great, Rick. Thank you. And again, thanks again for presenting your slides and answering our questions. Any questions we didn't get to, those will be answered later. The contact information is up on the screen again. So, for those attending this afternoon session, you can contact FANUC if you'd like more information by using that contact information. So again, we really appreciate the time all of you've taken to be with us this afternoon, and certainly hope you found it worthwhile. Thanks for taking part. Again, my thanks also to those who arranged this session, helped it go really smoothly. So this concludes our webinar. Have a great day, everybody. This is Mark Albert at Modern Machine Shop Magazine, signing off.